And our next speaker is Shannon, and I believe she's going to talk about the ridge leverage score sampling ridge regression for genetic data.
Yeah, biological data.
Great, thank you very much.
Yeah. So, hi everyone. Thank you for having me. I thank the organizers for inviting me. So I'm Shannon McCurdy, and I just joined Ancestry.com as a statistical geneticist. But until recently, I was a computational biology postdoc here at UC Berkeley, and I was co-advised by, co-mentored for my postdoc by Leo Pachter and Lisa Barcelos. And just so you have my full history, full disclosure, my PhD was in physics. So I've had wide and varied interests. And the work that I'm going to talk with you about today is work from the end of my postdoc, and it's on ridge regression and deterministic ridge leverage score sampling. And this work is on the archive and to appear at NIPS. And so just a high level overview. People here, even in this room, have considered randomized sampling with ridge leverage scores. And people in the community have investigated deterministic sampling, though not with ridge leverage scores. And so I sort of brought those two pieces together to think about deterministic sampling with ridge leverage scores, and then hopefully brought it to in an even new direction, pushed things forward in a new direction by pairing this ridge leverage sampling with ridge regression. So that's just a high level. So I'd like to give you some motivation at the back of my mind. I always have this problem that I have moderately big data. So what do I mean by moderately big data? It's too big to really inspect by hand, but you aren't limited by the memory of your machine or the computational time for your algorithm. So here we're thinking also that our data is in the high dimensional regime, so we have many more features than we do samples. And this area occurs very frequently in biology, where we have a data matrix A, where we have at the rows of the data matrix are samples, and these are from individuals or from tumors or from cells, and the columns are different features that come from, in my case, genomic data. So this could be a single nucleotide polymorphisms called SNPs, which look at different loci in your genome. It could be gene expression signatures, could be mutations, methylation. Our ability to collect very genomic data is very large for a single sample, but we don't always have nearly as many samples as we do the ability to collect biological data from that sample. So this case occurs, and so we've measured all of these features, but this question that I have is maybe not all of them are important. So we could reduce the dimensionality of our problem by doing something like SVD or PCA on our data matrix A, but the linear combination of columns that we would get when we reduce our data matrix to this smaller feature set is not very interpretable for a biologist who's interested in finding a set of genes to interrogate, for example, as being important for their system. So interpretability is really important, and we'd like to perhaps, instead of getting linear combinations of features, we would like to know exactly like a subset of features. And so to do this, we need some way of ranking and selecting columns. And so this high-level question in the back of my mind is, can we select columns of this data matrix A, which and create from that a column submatrix, which I will be calling C, that preserves nice properties of A. And I'm going to unpack each of those bits of the statement throughout the talk. And so then once we figured out which columns in A are important, we might also want to do something with those columns, and that's something that I'm going to consider doing is ridge regression with this smaller feature set. So to get there, I'm going to talk a little bit about leverage and some different flavors of leverage. Then just very briefly, deterministic versus random. I'm going to talk about some bounds that come out of this procedure and some experimental data from tumor samples at the very end. So classical leverage scores, or the leverage scores that were first introduced in the literature, They measure the importance of each column, which in my case is a feature, in the column space of A. And so this is a really nice intuitive definition, which some people in the audience, Cameron and Chris, are part of introducing this definition of leverage scores. You can see that, that the leverage score sort of captures how easy it is to write a single column of your matrix in terms of a linear combination of the other columns in your matrix. So if this problem is easy, if it's easy to write one column as a linear combination, then tau is small. If this problem is hard, then tau is large. And tau ranges from 0 to 1. And tau is your leverage score.
Is that unique?
Yes.
No, but the X that obtains it, is that unique?
I believe it is.
It is. This is the
Yeah.
this is just
I know
the
the norm is unique, but the X that attains the norm, the
Well,
linear
if
combination.
if all the columns of A were the same.
If all the columns of A are the same, then X is equally weighted in all of its components. And so the leverage score is something like 1 over the number of columns.
X is unique. X is unique.
X has
If A is full rank, it's unique.
Yeah. If A is full rank, and so you have to if you are in the case that
I'm
A.
not trying to distract you.
Oh, yeah.
We can talk about it offline.
Well, you can write this a little bit more carefully if A is not full rank, and then you have
I'm
to.
not concerned.
Yeah.
Never.
Okay, sorry. So an alternate and equivalent definition, which is maybe more familiar to people, is the leverage score, where you think of the leverage score as the norm of each column of A with respect to this inner product, where the matrix that you're using to take your inner product with
So
respect
you're
to.
getting a minimum known solution. Okay.
Yeah.
Not a solution, also.
Okay, so you're sort of measuring the length of your columns with respect to this norm given by the A transpose of your complete matrix and its inverse or pseudo-inverse if A is not full rank. And so if you recall your singular value decomposition, you can rewrite your leverage score yet again as a sum for each row. For each row in your left singular vector, you sum over the columns of the truncated left singular, right singular vector V. And so, you sum over the columns. Make sure I said that right. You sum over the columns of the matrix of the right singular vectors. Okay, this is a leverage score. What has it been used for? Well, as I said, it quantifies the importance of each column I in the range space of A. And so they've been used in regression diagnostics, outlier detection, and randomized matrix algorithms. And historically, leverage scores were used to select informative samples. But as the case where we're collecting many more features than samples has occurred, they've also been used to start picking informative features, and the informative features setting is the one that I'm interested in. So if you look at this expression, you see that the right singular vectors are kind of important for the leverage scores, and this begs the question: are all of the singular vectors important in your mind? Are they all equally important? And so perhaps if your spectrum looks something like this, you may not care about all of the singular vectors. You may not care about the ones with small singular values. And so you're left with a question, well, how do I want to treat these singular vectors with small singular values? Do I want to omit them or do I want to dilute them? And both approaches have been taken in literature. So the first approach is to just omit them. And if you do that, you're led to rank K subspace leverage scores. And so there you just project onto your matrix, onto the top K singular components, and you use that to take your norm. Well, semi-norm, because there are these, it's possible to get zero directions. And so what this does in your leverage score is it says, all right, I'm going to continue to sum over my right singular vectors, but I'm only going to sum over K of them rather than all n of them. And so you can create this really nice geometric picture where you've sphericized the columns of your data. And so each column is a point on this, and the leverage score is essentially the radius of the column on this picture. So large leverage score columns are ones with large radius. But this approach has been noted in the literature that this taking the projection onto the top k singular vectors of a matrix is not always unique, and it can be sensitive to matrix perturbations, and so it's sort of not a very stable operation to do. And moreover, your norm here is not full rank, so maybe there's something that's a little bit more natural. And so that leads to the second approach, which is instead of omitting these directions entirely, we are going to just dilute them. And so we have our AA transpose in our pseudo-inverse, and we're going to regularize it by adding a piece that's proportional to the identity so that this matrix now becomes full rank. And for the purposes of this talk, I'm always going to take this regularization parameter, which is proportional to the Frobenius norm of the complement of the top k singular vectors that we care most about, because that gives the available bounds. But so we can sort of complete our matrix by adding this portion proportional to the identity, and we're going to say this is how we're going to measure distance. And so if you use your SVD, you can work out what these components are, and you can see that now, and if we, now what we've done is that we have these singular values, but in the denominator, we've added this piece, which is proportional to the regularization parameter, which means that the small singular values matter less proportionally than the large singular values. And you can draw a similar picture, except for now contours of constant leverage are ellipses rather than circles. So these leverage scores are very nice because they are they sort of address some of the problems that came up in the rank K leverage scores. They're much more stable, and they behave a lot more predictably if you do matrix perturbations, and they change monotonically if you add or subtract columns to your matrix A. And this is work by the Musco brothers here and Michael Cohen, who made this important realization. And then also Michael Mahoney and his collaborator recognized that ridge leverage scores were very natural in the context of kernel ridge regression. So ridge leverage scores, hopefully I've convinced you, this is a very sensible quantity to look at. And so this is the quantity that I'm interested in for you in how I'm going to rank and select my columns in my algorithm for choosing a column subset. So deterministic versus random. I'm here at a randomized numerical linear algebra conference telling you about a deterministic algorithm. So why am I doing that? Well, the main reason is interpretability. And so biologists, not just biologists, but people in general, do happen to like if you run a procedure or an algorithm, you will get the same answer every time, so you have some confidence in your results and what they mean. There's no failure probability, and then under certain conditions, which I'll touch on briefly through my talk, like the bounds that are actually available if your data has a certain signature. So this is why I'm interested in a deterministic algorithm. Also, I'd like to make the pitch for pure curiosity. There were these nice bounds for randomized algorithms for ridge leverage scores, and the question that I was curious about was like, well, can you do this in the deterministic setting too? It seems like you really should, but nobody had done it, so.
Sorry. There
Yes.
are lots of algorithms for subset selection, deterministic algorithms. And even in the deterministic sense, if you could do everything in exact arithmetic, the solution is not unique, because if you change, say, just the columns of your matrix and run the algorithm again, one gets different different selection of columns. They may have the same properties in terms of singular values, but they're different.
Yeah, so I think the
So
argument...
there's a lot of work in numerical linear algebra for deterministic algorithms.
Oh, okay, great. Well, I would love more pointers to the literature. You can
Actually,
let me know later.
Who has worked on this? I don't know whether he's here. Yeah, he's...
So, yeah, so do let me know. So the deterministic sampling algorithm in this talk is based on work by Papayolopoulos. I apologize if I mispronounced his name, and his co-authors. And so basically what we're going to do is we're going to calculate the ridge leverage score for each column. And we're going to line up all of our columns according to their ranked ridge leverage score so that they decrease. And then we're going to be greedy and we're going to take all of the columns that have large ridge leverage score and we're going to drop all of the columns with small ridge leverage score. And the real power in this algorithm is that you can add up the leverage scores of all of the columns that you've dropped, which is sort of this area under the curve. And that's proportional to the error that you're going to get in your later bounds and norm. So this algorithm was introduced for rank K subspace leverage scores, and it just takes a couple adaptations to make it work in the setting of ridge leverage scores. But the ridge leverage scores give you a much richer set of bounds, essentially because you have regularized your matrix with which you're taking your inner product. So that brings me to the bounds. Like, what can we do with this? And so these are these nice properties that we're thinking of when we're trying to select the columns of A. Like, what are we preserving about our matrix A when we do this? So the first property, and the one that I'm going to talk about in more detail in the next slide, is a spectral bound. And this is an extremely powerful tool, so I'll talk about it next. Another property that we might be interested in is column subset selection. And this, in my context, is used as a feature selection algorithm. And the idea here is that you want to find a small number of columns that approximate the column space of A nearly as well as the top K singular vectors of A. So this is a question that has been interrogated before with leverage score sampling. Then there's also rank K projection cost preservation. So bounds of this type are important because they mean that low rank projection problems can be solved with your column subset matrix rather than your full matrix, and you're still preserving the cost, the projection cost. And this has implications for k-means clustering because the k-means objective function can be written in terms of a projection matrix. And this has been interrogated before, again, for randomized ridge leverage sampling. And the question was, can you get a similar bound for ridge leverage scores? Or sorry, for deterministic sampling with ridge leverage scores. And then lastly, there's a question of what are the number of columns selected? Can this ever be better? Can the bounds on deterministic sampling ever be better than the available bounds on randomized? And this was a question that was interrogated in terms of rank K leverage score deterministic sampling, but was unknown for ridge leverage score sampling. And so, of course, the answer to all of these bounds is like, yes, they exist. This is possible for deterministic sampling with ridge leverage scores. I'm not going to write them all out formally. Instead, what I'm going to tell you is a little bit more about is the spectral bound, which is the most powerful among them and allows you to get a lot of the other results. So the spectral bound that we have is that a column submatrix of C from A selected with the deterministic ridge leverage score sampling algorithm that I sketched for you briefly before will obey the following property. That column submatrix C is less than, so C transpose is less than A transpose on the right and greater than this quantity on the left. And so this is an additive multiplicative spectral bound, and I should probably explain for you what is this symbol here. So this symbol here, this less than or greater than sign, is called a Loeffler ordering, and it's a generalization of the real line to Hermitian matrices. So what this means is, just like for real numbers, we know that 2 is already greater than 1.5, always greater than 1.5. You can say that a matrix is greater than another matrix if it is Hermitian and dot products with respect to that matrix, if a dot product for all vectors x with respect to one matrix are less than dot products with that same vector x with another matrix, then the matrix for which all dot products are greater is greater than the other matrix in the Lohner ordering. So that's a lot of words. So I will write that down. If you have F,
You can't see that. Oh,
is that not visible?
the ink isn't so great.
I think this audience is comfortable with this notation.
Is everybody here good with that?
I think so.
Okay, so
Can I ask a quick question? Is lambda 2 the value that Chris and Cameron have in their
Yes.
paper? So just that value.
Yes.
This is not true more generally.
so this, I didn't think about trying to vary lambda 2. That value of lambda 2 is definitely very important for the,
In the proofs. Yeah, we
Yeah.
see that too. Yeah.
yeah. Okay, so the Lohner ordering, the reason why it's so powerful, it gives you ordering on eigenvalues, ordering on traces, ordering on distances. So this is a very nice thing. And I should also mention that this is the bound that holds if you've chosen C with a randomized algorithm and you've reweighted your columns proportional to the leverage score, which is proportional to the sampling probability. So you can see that the bound on the bottom is the same, but the bound on the top is a little bit worse, and that's because of the randomized sampling.
So are you interested in A or AA transpose? You're interested in A, right? Because that's your data matrix?
I think it sort of depends on what you're interested in doing. Oh, me?
Yeah.
I am interested in the singular values, and I'm interested in doing ridge regression with A. And it turns out that bounds of this type, which hopefully I can get to by the end of the talk, actually this is a very powerful statement that allows me to talk about ridge regression with A. So you'll have to hold on just for a little bit to see where that goes. So just to give you some intuition, the top part you basically get for free from your selection matrix, so I won't talk about that. The bottom part is a little bit harder to get, but not very hard. Basically what you do is you look at the difference between AA transpose, and you decide that I'm going to multiply on both sides by the identity matrix, but I'm going to write the identity matrix in a special way. I'm going to break down the identity matrix into U bar sigma, where this is your singular value matrix, which has this extra bit added to it, and this is invertible, and U transpose. And U transpose because I have all n components, so this is square, so this is equal to 1. So this is what I'm going to call my identity matrix. I'm going to multiply from both sides. And then this piece, so this is U, sigma bar, inverse, U transpose. And then I have this piece in the middle. And then I'm going to call this quantity Y. And if you were doing randomized sampling, you would use a matrix Berenstein bound to bound Y. But it turns out that when you're doing this deterministic sampling, you can bound this quantity by taking the trace, and that's proportional to, or that is the error for the leverage scores that you have left out. So this is nice because you can just actually do this.
So 5 minutes.
Thank you. So I talked about nice properties of A, like column subset, projection cost preservation. Yeah.
Sorry, how many columns do you sample to get that kind of problem?
I'll give you like, okay, so actually, let's see, I have that. The expression is a little bit messy. So maybe what I will just tell you rather than to take the time to write that out is that if you have in a particular setting where your leverage scores decay with a power law profile, then you can bound how many columns you choose with this algorithm. And if a coefficient in that power law decay is greater than 2, then the number of columns just deterministically sampled is order k. And so you can write an exact expression, which is a little complicated, which I can write at the end, which basically shows you when you will choose fewer columns with deterministic sampling under power law decay compared to the randomized algorithm with the same level of error.
That would depend on epsilon.
And it depends on epsilon, yeah. So my problem that I'm interested in is ridge regression. So it's used to solve regularized ill-posed least squares problems. So in contrast to the other talks, I'm interested in choosing fewer features, not choosing heavyweight samples. So my selection matrix goes between A and X rather than on the left. And so this is the ridge regression problem. I'm short on time, so I won't talk about it in super much detail. But basically, you have your least squares problem, and you have this regularization term, and there are these exact solutions. And so if you have a model for data generation where you don't actually observe y, which is this function of coefficients x times your matrix A, but you observe a noisy version of it, you can calculate what the risk of the estimator is for ridge regression. And this is, my question was, well, what if I use my submatrix C to do ridge regression rather than my full matrix A? What sort of error do I get? And so other people have done a really nice massage of this ridge regression risk. And it goes, as you might expect, into two terms, a bias term and a variance term. And you can see that this bias term has a very subjective form. You can see why these bounds on A transpose are important. We can use our bounds that we've derived for C transpose in terms of A transpose to bound the quantities of the bias and the variance. So we use the bounds, which I've only told you about, but all the details are in the paper, to bound this risk. So the bound exists. It's multiplicative in this form. There are constants. You can figure out what they are. And you can compare to the elastic net risk. So basically what you're doing by doing column subset selection is you're forcing 0 entries in your matrix. These are the areas that your matrix are not sensitive to the coefficients, so you're setting them to 0. And then you also have the shrinkage for ridge regression. So it's a different way of getting sparsity. So experiments, I have slides that are essentially, I think, going to just tell you, you can choose very few features out of 70,000, you choose 1,500. And there are biological signatures in the data which are meaningful. Your ridge regression does a good job whether you use C or A in predicting this biological feature. And I'm happy to tell you more about these experiments offline to not take too much time. So I really appreciate your listening. These were my postdoc advisors. I'd also like to thank Michael Mahoney and his group for listening to me talk about this work, my Ancestry.com for supporting me in being here, and you folks for listening. So
Thank you
thanks.
very much, Aldi. One or two quick questions? Jeff?
I was wondering if you can say just quickly how it compares to doing the randomized version, using kind of experimentally.
Oh, I can't say. Yeah, I'm not sure. That wasn't a comparison
I
that
have
I
a very
did.
short answer to that. Biologists
Yeah.
do not like random selection.
Yeah.
So when we did those things on SNP data,
Right,
deterministic feature selection with respect to leverage course is what we did for bio journals. You cannot do randomized selections there. Numerically they're interesting, but not for practical.
Is because the editors, the journals don't like it, or because
Because the
proponents?
community doesn't like to run the same algorithm and get 10 different groups of features that they cannot improve. They want one group.
So you mentioned in the spectral bounds discussion that when you do randomize the CC transpose matrix, the columns are reweighted, the selected columns are reweighted. So implying that for the deterministic case, they're not
No,
reweighted.
they're not reweighted. Yeah.
I see.
Just specify random.
And
In the application in the regression, See, the issue is that the variables are selected in your method before seeing the y.
Yes.
So the comparison with elastic neg has to be a bit, I said, it's hard to make a comparison because in the lasso part, the elastic net actually sets some variables to 0
Yes.
by looking at y.
Right. Right. So there's two different ways you can set the coefficients equal to 0. So the lasso looks at y. This procedure doesn't look at y. It looks at the structure of A and says which components of my regression coefficients am I just not sensitive to in my matrix. Essentially, can I solve them by changing the weights of my other coefficients?
Okay, but you have this down the risk, which is not. I mean, it's great. So you can do well at prediction, but at variable selection, I would think, there's a grain of salt there,
Sure.
because again the variables were selected before even seeing y. So that's.
Yeah, I think that's interesting, isn't it?
You have to be really lucky. No, but,
Isn't that what basis pursuit does? It takes into account the y. No?
Yeah, but this.
Yeah, I agree with
Okay.
you. I'm just saying.
So people have done that in the past where they applied PCA first to dx and then did regression, and that's typically terrible because again you have to guess. Essentially, you're guessing what variables are important before looking at the y. So
But
I'm
I
just
mean, here
saying,
she has a short and fat matrix.
Yeah, short and fat. So I'm saying which features are essentially easy to write as linear combinations of other features. So like this is, yes, it's not looking at y, but it's looking at a, and a matters in the regression too because it's a dot product of a and x.
I'll take the line if you guys don't mind. I need to get people out for coffee. Thank you very much,
Yeah,
Shannon.
thank you.
And we are recording